Is this working? While we set up, I'll introduce our next speaker. Our next speaker is Professor Zheng, who is currently the professor and department chair of statistics at Columbia University. She also did her PhD at Columbia. Professor Zheng's research has been recognized in many, many ways, including becoming a fellow of the American Statistical Association in 2014, the Mitchell Prize from ISBA, the Statistical Application Award from the American Statistical Association, and many others. She really exemplifies the idea that statisticians get to play in everyone else's backyard. She's done work in genetics, climate modeling, understanding fatal drug overdoses, and today she will be speaking to us about prediction scoring of data-driven discoveries from reproducible research. Please welcome Professor Zheng.
Thank you. I just want to start by reading a little bit of reflection I wrote when I was listening to the morning session. I think in statistics, being a statistician, we care about learning about variability. One of the things we celebrate the most in statistics is the variability. And then we model it using probability distributions. And then to think about it, stability is a feature of a distribution. So Bing's VPS framework, which I personally feel like responsible promoting because I'm responsible for the first word, provide a formal guideline to think about the statistical or stochastic behaviors of our data science research. To think about data science research as some center of research itself, the behavior of our research, and then study as a subject. Stability is a way to think about this. And then because this research has been increasingly driven by randomness of data collecting, data generation, and data analysis itself. And so therefore, for my talk, I think about reproducibility. I want to argue that reproducibility is hard to study or even improve if we don't think about how to measure it. So in this talk, I want to talk about one project I did a few years ago to think about prediction scoring, how to measure predictions in the hope of improving reproducible research. So this was part of a big project. I don't know how many of you have saw this project. It's a DARPA's effort in social science. It's the next generation social science. And then that project invited all the team to collaborate and then even try to require that one team make prediction of other team studies. So to simplify, it tried to say that, say you want to have pro-register report for your study, and study one is try to make prediction about what's going to happen for the reproduced study, and then study two, you're supposed to score the predictions generated by study one using data collected in study two. So the goal is that they're not trying to say that the result is reproducible, but they're trying to say whether we can derive insights from such effort on the underlying data generating mechanism. So the data generating mechanism is our goal of study. So one of the motivating example is from one of the team is a collaboration between Yale University and the Gallup, the pool company. And where they consider a simple game is a public good game, where multiple players join a game together, and for each round, every player only have two actions to consider. One is to contribute, the other is to defect, not contributing. And then you play a fixed number of rounds, and then each player goal is, of course, to collect as many tokens as possible. And you know that if that's the case, then you should always contribute. But if people see other people not contributing, they will choose to defect. So you always go that way. So the game have several conditions that you have. They have fluid, random, static, and viscous. And then the study one shows very interesting. Is a typical published study where it shows that you can see a pronounced difference between the full settlement. The full settlement concerns whether the player, after seeing defects of other players, can choose to regroup, right? Imagine you are in a course project. I know some student in the audience, you're in a course project, you see your teammates not contributing, and you can say, I'm not going to do the project with this person anymore. I'm going to change team. So the fluid is you can change more freely. Random is that the professor says you guys not working together, we just shuffle it up and then reassign you to a team. And then static is that you're stuck with your team forever for the entire course. And then the viscous is something even changing even, I think it's smaller, the 10% change. So they do, in the original published study, they do see the difference across the four in terms of the rate of contributing, where they try to replicate it using new players around the world and the international participants, and then see something not as regular looking as the previous published study. So in a typical setting, if you want to evaluate the prediction, what you want to do is that you have an original study and then you have a new study. The question is, are they the same generating mechanism? And then you have the model, you use, oh, sorry, the cursor is not working. So you're looking at the model fitting software, and then you generate the prediction and you do a prediction score. So one example is that you try to fit a simple model, assuming you have a nonlinear generating family, and each data generating mechanism differ a little because it's always the truth. In reality, in practice, you cannot assume everything remain the same. They always have difference. And then the question is, can you reproduce it? So here is if you predict, you're able to reject non-hypothesis, and then the prediction score could be that you reject the non-hypothesis. That's the original intention. However, in reality, is that we need to consider that there are possible noises and randomness in the model you fit. What if we are not just running logistic regression? What if you're doing random forest? What if you're doing MCMC or large language models where you know there are innate randomness even when the data remain the same? And then also whether we can think about from a yes or no, whether it's reproduced or not, into some kind of measure of distance if you know for sure the model has changed. So we decided to propose a framework where we want to just leverage one of the classic statistical idea of resampling, try to emulate some randomness of data sampling, separate the data sampling randomness from the data generating mechanism distance. So there's a few distance we try to measure here. One is the true distance between the two data generating mechanisms that we're interested in. We worry that distance is being clouded by randomness in the sampling randomness of the data and potential randomness in the model. So what we do is we use the data from study one and then use cross-validation, which is using subsampling, resampling of the original data. And for the new data, we apply similar sampling and also generate validation statistics. So what we did is we changed from 1 point from the study one and 1 point from study two, using sampling and resampling to create randomness due to sampling. So then we try to compare distance in a distributional fashion to allow us to answer the question, are these two data generating mechanisms truly different? And then we also realized when we're doing this is that the model actually play a role in this whole question about whether the two data generating mechanisms are the same or not. We found that actually it is when you do, anytime you do a scoring of this kind, you are actually projecting the true data generating mechanism into the space of prediction space according to a model. I realize this when the DARPA program require us to say you want to be able to score your prediction, and I said if I use a really lousy model for my data where have no significance, and then I know the really lousy model will also have no significance for next study, my prediction will always be true. So therefore, we realize there's a role that the model plays. To demonstrate the role of the model, we run some simulation. Here we try to imitate what the game play. We assume there's a human, there's potentially a bot, and we estimate this coefficient based on human players under different setup, and then we fit a different model to the study. So we see that there are different behavior for sure, but by fitting different models and using the cross-validation and validations, we can see that this is where the two data generating mechanisms are exactly the same. This is where the two data generating mechanisms are different. And then you can see that according to different models, the two studies look similar or different to a different extent. So what we did is we replicate this many times and then use this on this axis. This is the presence of a bot in the simulation, and then we just we calculate how this true difference of the generating mechanism associate with the distance between the ROC curve here, and then we plot this using distance correlation to see that model 1, the first model, capture the distance better than the other two models. And then we just want those, And then we apply this to a real data. We found something in addition to that is that if you measure the prediction using different metrics, one using ROC, the other using the area under the precision and recall curve, you actually have different conclusions that you can have. So these two studies look very similar on the ROC, meaning that even there is a difference into the contribution rate, then it's still predictive of behavior of the human players. But the precision recall curve tell different story because the baseline contribution rate are different from the two games. And so so if we care about whether there are treatment effects to the players, we want to control, we want to eliminate effects of the baseline. So we use, in the resampling, we oversampled, we adjusted weights for the contribution and rerun the model, and we were able to show that after account for the marginal contribution rate, we're able to conclude the two games even look different on the contribution rate, but the human behavior under different experiment setting are actually rather similar. So to conclude that in this project, we try to think about a reproducibility study, measure reproducibility using a score of the prediction on a continuous scale. And then we want to view it as a distance between two data generating mechanisms projected into a model space, and which allow us to take into account uncertainty due to sampling and all this algorithm randomness in the modeling process.
Thank you. We have plenty of time for a few questions.
So I have a question. For example, if you know you have the data 1, data 2, right? For example, if you want to do, I have whole data, right? Just separate it 2 parts. So what kind of difference? So you can say if I have whole data, then have 2 groups, but that's more homogeneous, right? But they have 1 data 1 versus 1 data 2, right? With much heterogeneous, right? So if that way, so what kind of difference in your prediction?
So so for the same study, you want to do data splitting?
Yes.
So we sort of already doing that for the cross validation. So here we actually leverage on the data splitting to estimate how much sampling variability one can get by doing subsampling. And then one thing I didn't have the time to dive into is here that the other way. So it's here that when you try to do the subsets and the subset here, in order for us to eliminate the effects of difference in sampling design, we make sure when we produce the subset, they are exactly they use the exact same sampling scheme. So we already leverage on the data splitting here for the same study.
Yeah, so if that way, you can say in the 1 and 2, right? Your simulation setting will be different for 1 and 2, or just same. You can say, for example, now you have experiment 1, right? Experiment 2, right? Mm-hmm. When you do the simulation study, right? Basically, you have need a setting for 1 and 2, right? So your setting will be same or just will be different?
For the setting,
Yeah,
the simulation, we
Yeah.
actually, so here, oops, sorry, not very familiar with PowerPoint. So here, this one, the two, so our setting is that we want to simulate different number of human and bots in the study, and then the first simulation is like under the null hypothesis when the two DGM are exactly the same, and the second one is when they are different.
Okay, I see. Thank you.
I would actually, may I ask a question? If I understood right, the way that you account for sampling uncertainty sort of depends on an assumption of exchangeability. And I wondered if you could briefly discuss how you might modify this to address, for example, Professor Kadran's setting where you've got geographic or possibly highly correlated data.
Right. I love this question because I think exchangeability, like if you understand what is exchangeable, then you understand what the model is doing. So for this one, that this is a perfect example that you could. So for the first one, that we just assume all the player exchangeable. So we are just gonna shuffle them up and then resample, and then but the two games are different. Under the second game, we don't know what happened. Maybe because it's an online game or because it's international crowd, people were too cooperative, and so when you sample that, you see the difference. But we adjusted for that by using weights. We could also, but when you use weight, you can also do subsample, right? You can classify the player into the one by the way they contribute, and then doing stratified sampling to balance study, making sure the subsets are comparable in terms of their baseline contribution rates. So that's what we did. It's basically like kind of a parametric bootstrap idea.
I'm curious how you would interpret the output of the analysis. Like, you can estimate the delta DGM. That means the two distributions are different, but it doesn't necessarily mean the predictions are different. And once you see the difference in the predictions, would you prefer a model with a prediction difference that is highly correlated with the distance in distribution, or would you prefer a model with a smaller correlation because that seems more stable?
Right. So there is a new paper come from Duncan Watts. I just attended his talk last week, and he's talking about a prediction culture versus explanation culture in computational social science. And I thought for this particular study, we're looking for the explanation culture. And then here, when we have the three models, and we saw that the model one has the biggest difference between the different studies is that we realize that when we introduce when we shift from human-like behavior towards boss-like behavior, their behavior differ the most in terms of how the behavior change over time. So that's what we thought. It may not tell you exactly what the model is because we're fitting totally different model than the ground truth model, but it does generate insights. So that's what we hope to generate.
Thank you.
All right, let's take our speaker.